All right, chemistry, let's take a look at the second part of our video lecture for chapter 15. Last time we met in video form, we talked about the Arrhenius theory for acids and bases, the Arrhenius definition of what it is to be an acid or what it is to be a base. Today we're going to add to that the next version of what it means to be an acid or a base, a different definition of what it means to be an acid or a base, the Bronsted-Lowry acid and base. So today I want you to be able to define and recognize Bronsted-Lowry acids and bases. Then I want you to be able to define and relate conjugate acids and conjugate bases. Then I want you to determine the formula for the conjugate acid of a given base and for the conjugate base of a given acid. And this next one's going to be a little bit of a mouthful, but it's actually fairly simple once you get your head around the words. Explain why the conjugate base of a strong acid is a weak base, and why the conjugate acid of a strong base is a weak acid. And then lastly, explain what determines whether an amphoteric compound acts as an acid or a base would be the other option. So let's go and get started. Now, a Bronsted-Lowry acid, again, this is going to be slightly different from the Arrhenius definition of what it means to be an acid, but it's not wildly different, so see if you can keep up. A Bronsted-Lowry acid is a molecule or ion that is a proton donor. Remember, a proton is the same thing as the hydrogen ion, because a hydrogen ion is a lone, all by itself, proton. Remember, hydrogen is atomic number 1, and so it's going to have 1 electron with it, right? 1 electron with 1 proton. Well, if that hydrogen atom ionizes, it's going to lose that 1 electron that it's got. So it'll have no more electrons. It'll just be the 1 proton. Right? So proton donor, an H plus donor. Hydrogen chloride will act like a Bronsted-Lowry acid when it reacts with ammonia. Now we look at this equation here, and like I mentioned last lecture, this G with a hat on it, for some reason, the weird formatting issue, this is supposed to be a negative. Right? This is the chloride anion. It's got a -1 charge. But for some reason, whoever made this image, I did not make it, there's a weird formatting issue, and I can't fix it because this is actually an image right here. I can't get in and change the text. It's actually just a picture. So these G's right here, these capital G's with the little hats, those are actually supposed to be minus signs. But hydrogen chloride acts like a Bronsted-Lowry acid when it reacts with ammonia. Here's the ammonia, here's the hydrogen chloride. So in this situation, the hydrogen chloride is going to act like a Bronsted-Lowry acid. What does a Bronsted-Lowry acid do? It is a proton donor. So what is this going to do? Donate a proton. And so when the reaction occurs, this is the proton right here, this hydrogen. It's going to ionize, it's going to pop off, right? And it's going to add on to this ammonia. So now notice that the ammonia has gained that hydrogen proton, and the chloride anion is left all by itself. Right? So in this situation, HCl is the proton donor. It's donating the proton, donating the hydrogen. Is a Bronsted-Lowry acid. Water, right, the most neutral thing ever, can act like a Bronsted-Lowry acid. How does that happen? Well, let's react it with ammonia. Ammonia is, a nice base. What's going to happen? This proton here is going to be removed from the water, and it's going to be donated to this ammonia. Right? Notice how after the reaction has occurred, there's 1 less hydrogen in this water. Well, it's not water anymore, but this hydrogen got booted, so it's just OH by itself. OH minus, a hydroxide polyatomic ion. And that proton has been added to the ammonia to make it NH4 plus, which is ammonium. As we move forward, a Bronsted-Lowry base is a molecule or an ion that is a proton acceptor. So that's going to be the opposite of a Bronsted-Lowry acid. Right, when Bronsted-Lowry acid was donating a proton, the base is going to be accepting that proton. We already saw examples of Bronsted-Lowry bases on the last slide. We were just focusing on the acid. Ammonia, which is what we used in the last slide, accepts a proton from the hydrochloric acid, and it acts like the Bronsted-Lowry base, because to be a Bronsted-Lowry base, you're accepting the proton. And so let's look at the exact same equation we just looked at. Again, this is a Bronsted-Lowry acid because it's going to be donating this hydrogen. Well, where's the hydrogen going? To the ammonia. It's the ammonia that's going to accept that proton to become NH4 with a plus. The hydroxide polyatomic ion produced in solution by Arrhenius hydroxide bases, like for example NaOH, is a Bronsted-Lowry base as well. Okay, so the NaOH, which is the Arrhenius base with the hydroxide, because when it dissociates, it generates the Na plus and an OH minus. That OH minus can accept a proton. What will it be when it accepts a proton? It'll be water. It'll be H2O. H2O, because it gained the proton, the hydrogen ion. And so that OH minus can accept a proton, therefore it is a Bronsted-Lowry base. Oh, too fast. In Bronsted-Lowry acid-base reaction, so when we are reacting Bronsted-Lowry acids and Bronsted-Lowry bases, protons are transferred from one reactant, which is the acid, to the other reactant, which is the base. Right? So we're transferring from the acid to the base. And so, again, looking at this same equation, yes, this G is supposed to be minus, right? It's chloride with -1. The proton is going from the acid to the base, right? From the HCl to the ammonia. This hydrogen is going from this molecule to this molecule.
According to the Bronsted-Lowry definition, an acid is something that can donate a proton. The acids described by Bronsted-Lowry are all molecular compounds with ionizable hydrogen atoms, like this hydrogen chloride. A Bronsted-Lowry base, on the other hand, is something that can accept protons.
So again, this is that representation, HCl with the NH3, Bronsted-Lowry base, Bronsted-Lowry acid. Now let's look at particular types of acids, monoprotic and polyprotic. If you have a command of the English language and various root words, suffixes, prefixes, this will be easy for you. A monoprotic acid is an acid that can donate only one proton. Remember, the Bronsted-Lowry definition of an acid is that it donates protons. So a monoprotic acid is a Bronsted-Lowry acid that can only donate one proton. Mono, one, protic, proton. One proton acid. All right, so we have a few examples. We have perchloric acid, right? There's only one hydrogen to ionize. Hydrochloric acid, there's only one hydrogen to ionize. Nitric acid, there's only one hydrogen to ionize. Monoprotic acid. So there's only one ionization step because there's only one thing to ionize. So we look at these two representations of acids. We have a monoprotic over here. See, that's one hydrogen right here, one proton, monoprotic. As opposed to this sulfuric acid, see how there's two H's. Two H's. Now this is a strong acid. This is going to dissociate completely. It's definitely going to give off one of those protons to form a hydronium ion, and then HSO4 with a -1 charge. Now this, okay, this right here, this HSO4 -1, is a weak acid, but it's an acid nonetheless. This proton can still be ionized to generate a hydronium and then just the sulfate anion by itself. But again, two protons, so it's diprotic. Di referring to two, protic referring to protons. So polyprotic acids are acids that can donate more than one proton. So monoprotic versus polyprotic. And so our examples of polyprotic, we have sulfuric acid right here and phosphoric acid right here. We've got two potential ionizable hydrogens and three ionizable hydrogens with the phosphoric acid. So there's going to be multiple ionization steps. Like we saw in the picture, this sulfuric acid is going to dump one of the protons, right, to form these products. And again, remember this G is just a -1. And so we're going to have this left over, where we're going to ditch one more proton to create a hydronium ion, and then sulfate with a 2-. Remember that G is supposed to be minus. So the sulfuric acid solutions will contain multiple species. Now, obviously, that's an acid, so there's going to be a hydronium in solution, right? H3O plus. Definitely going to be that because it's an acid. But it's also going to have HSO4 -1, right? The product of this first step. But then it's going to also have the sulfate polyatomic anion with a 2- charge, because that's a product of the second ionization step. Now, there will be a lot more HSO4 in solution than there will be SO4 because H2SO4 is a strong acid. It'll definitely donate 1 proton, but HSO4 is a weak acid, and only some of them will dissociate and finish up that ionization step. And so you might hear these terms as well, diprotic versus triprotic. They're just telling you how many ionizable hydrogens there are there. Diprotic, 2. Triprotic, 3 hydrogens that are ionizable. Now let's move on to a fairly difficult idea to get started with, but once you get it down, it's actually bananas easy. The species that remains after a Bronsted-Lowry acid has given up a proton, because remember, that's what a Bronsted-Lowry acid is, right? It's that species that donates the proton. Well, after that acid has donated the proton, what's left over is called the conjugate base. An acid has a conjugate base. And so here's our acid, hydrofluoric acid, which technically is a weak base, but you don't definitely want to touch it. It will melt you right quick. But after this hydrofluoric acid donates its 1 proton, it's just going to have fluoride ions left over, F with a -1. Remember, this G is supposed to be a minus sign. And so this fluoride is left over after the hydrofluoric acid has donated its 1 proton, because it's an acid, that's what it does. So this is left over. This is considered the conjugate base. Bronsted-Lowry acid-base reactions will always involve 2 acid-base pairs known as a conjugate acid-base pair. Right? There are going to be 2 of them, 2 acid-base conjugate pairs. So going back using that same equation, here's my hydrofluoric acid. This is definitely the acid. Well, that's going to have a base, a conjugate base after it's donated its proton. Well, this base, right? This base right here, right? If this is the acid, then water is acting like a base. It's going to accept that proton, right? It's the base. After it accepts the proton, it becomes the conjugate acid. The conjugate acid over here is the hydronium ion. So neutralization reactions, we'll cover this more in the 3rd portion of our video, but I do want to introduce this. If we have equal concentrations of hydronium and then basically the acidic portion and the basic portion of acids and bases, they will neutralize each other. If we have equal concentrations of those portions, we will neutralize the acid and base, and we'll just have a salt and water. So we need to talk about the strengths of conjugate acids and conjugate bases. The stronger an acid is, the weaker its conjugate base will be. The stronger a base is, the weaker its conjugate acid will be. So the stronger something is, whether it's an acid or a base, the stronger something is, the weaker its conjugate is. The weaker its conjugate, the stronger its original form. So we have HCl, which is one of our strong acids that we need to memorize. This strong acid is going to have a conjugate base, what's left over after it donates the hydrogen, which is the chloride anion, Cl-1. That G is supposed to be a -1. So strong acid forms a weak conjugate base, Now here's the original base and its conjugate acid, because this water is the thing that is accepting the proton there. All right, now if you need to press pause after I finish talking about this slide, please do so. It'll make a lot of sense if you just give it a few extra seconds of thought. Proton transfer will favor the production of a weaker acid and a weaker base. All right, so we have these 2 reactions that can go either way. Okay, they reach equilibrium, so they can go either way. When I look at these species, this first reaction, I see that this is a strong acid and a strong base. All right, strong acid, strong base. So the strong acid will form a weak conjugate base. The strong base will form a weak conjugate acid. Right? That's what we focused on last slide. This slide, what I want you to take away is, wherever the weak conjugate acids and the weak conjugate bases are, that's the direction that the reaction will want to progress. So in this first case, since the weaker acids and bases are on the right side, the reaction to the right is more thermodynamically favorable, which you don't really know what that means yet, but in the future you will. Whereas this second equation down here, over here on the right, these are actually the stronger acids and bases, at least compared to acetic acid and water compared to hydronium, right? So these two are the stronger by comparison, right? What are they stronger than? The things on the other side. And so the weak acid and the weak base is actually on the left side of this equation. So this reaction, the reaction to the left, will be more favorable.
Ammonia is a base. When ammonia reacts with water, water acts as an acid. Ammonia gains a proton to become an ammonium ion, and water loses a proton to become a hydroxide ion. The ammonium ion is the conjugate acid of ammonia. A conjugate acid is an acid that forms when a base gains a proton. The hydroxide ion is the conjugate base of water. A conjugate base is the base that forms when an acid loses a proton. When nitric acid reacts with water, water acts as a base. Nitric acid loses a proton to become the nitrate ion, and water gains a proton to become the hydronium ion. The nitrate ion is the conjugate base of nitric acid, and the hydronium ion is the conjugate acid of water. Acids and bases form conjugate acid-base pairs. Every acid has a conjugate base, and every base has a conjugate acid.
Thank you, Robot Lady. Well said. So here is a list of the relative strengths of acids and bases. So we have increasing strength of acids, increasing strength of bases. They are going in opposite directions because they are going down on the pH scale and then up on the pH scale. But we have things like hydroiodic acid. It's a very strong acid. Okay, perchloric acid, very strong acid. Hydrobromic acid, very strong acid. Right? Now the conjugates, if these are conjugates, these are going to be very, very, very strong. If these are conjugate bases, these are going to be very, very, very strong. A hydride ion, which is an H-1, which is a proton with 2 electrons, that's going to be a very strong base. Very strong base, because it's going to very easily accept another proton, which would make it a Bronsted-Lowry base. All right, amphoterism. Any species, any chemical that can react as either an acid or a base is described as amphoteric. Water is one of the biggest amphoteric substances that we are going to focus on here, because water can act like a base. If you put this sulfuric acid, which is a strong acid, in water, because water can act like a base or an acid, it has to do on what you mix it with. With this case, we've mixed it with a strong acid, and therefore water will act like the base, okay, to yield a hydronium ion and this conjugate base here. But water can also act like an acid if it happens to be more acidic than what it's mixed with. In this case, we're mixing it with a strong base, NH3, ammonia. This is going to be the acid. It's going to donate the hydrogen to go over here to make this ammonium, and then an OH -1. Remember, this G represents a -1. So water can act like a base or an acid depending on what it's mixed with. It's amphoteric. Now an OH group. Now this is not a hydroxide. This is not a hydroxide anion. This is an OH group. It's not an ion. It's actually attached to something. It's bonded to something. The covalently bonded OH group in an acid is referred to as a hydroxyl group. It's a functional group. Molecular compounds containing OH groups, hydroxyl groups, can be either acidic or they can be amphoteric. They can act as an acid or a base. The behavior of a compound is affected by the number of oxygens bound to the atom which is connected to the hydroxyl group. So let's take a look at a picture to see if we can understand this a little bit better. So here's hypochlorous acid. So we have an oxygen and a chlorine and our one hydrogen. Fair enough, right? Well, here's chlorine oxygen, hydrogen. This is the hydroxyl group right here, OH, right? No other oxygens bound to this chlorine. But we go over to chlorous acid. Here's our OH group, OH. Here's a chlorine, and now there's one oxygen bound to it. Go over here. Here's our hydroxyl group. Here's our chlorine. Now 2 other oxygens bound to that acid. And then lastly, we have perchloric acid. Here's our hydroxyl, our OH, our central chlorine. Now there are 3 oxygens bound to it. And it's the presence of these other oxygens bound to that central atom that are going to define the characteristic of that particular type.
Water can either be an acid or a base, and is therefore amphoteric. Like an acid, it can donate a proton. Like a base, it can accept a proton. Strong acids cause water to act as a base. In the first ionization of sulfuric acid, water accepts a proton from the sulfuric acid. Sulfuric acid is a stronger acid than water, so water acts as a base in this reaction. Strong bases cause water to act as an acid. In this reaction of water and ammonia, water donates a proton when it reacts with ammonia to form ammonium and hydroxide ions. Ammonia is a stronger base than water, so water acts as an acid in this reaction.
All right, chemistry, what we've done today is we've looked at the Bronsted-Lowry definition of an acid and a base. So now we have the Arrhenius definition of an acid or a base, and we have the Bronsted-Lowry definition of an acid or base. One has to do with increasing hydrogen ion concentration or hydroxide ion concentration. The other, today, Bronsted-Lowry, has to do with donating protons versus accepting protons. We have one more to add in addition to some other stuff, and we will deal with that next time we meet videoly.